Yeah, because today is very special. So many students do not come, but I'm very happy, so you all come here. But good thing is they can watch video. So for this situation, you know, we have the video, so they will not lose much. But I will delay attendance check next time. So today I do not check attendance. Yeah. Okay. All right. Examples, part 2. So we want to see more examples. Okay? Last time, the 3 examples too easy. So this time we will get a little harder questions. Yeah. Let's look at the first one. Actually, it is our question number 4 in this unit. Show that log of n belongs to little o of n. Actually, this one similar to one we did last time. Similar. Yeah. Little o, we need to calculate the limit. Okay? The limit, yeah, so let's do this. Yeah. All right, before we calculate limit, be careful. Remember, this n is discrete variable. If you want to use L'Hopital's rule, you need to use continuous variable. Okay? So we need to use x continuous variable. Okay? Because we plan to use L'Hopital's rule. All right? This is infinity over infinity indefinite form. Okay? Yeah, we just check a little bit. Infinity over infinity indefinite form. So we can use L'Hopital's rule. Yeah. All right. Let's take derivative. Yeah. All right. Yeah. So we have that. Yeah. Yeah. We assume hidden base greater than 1. Okay? A. Yeah. Otherwise, when you take derivative, what is the derivative? Right? You need to use that base number in your derivative. Okay? So based on the formula. The formula, okay? So I hope, but you can find that easily. Yeah. Then we simplify it, but this time it is not an indefinite form, okay? Indefinite form. Yeah, because numerator 1, it's not infinity, it's not a 0. Denominator infinity, but it's not indefinite form, okay? So we can get its limit immediately. Okay? Denominator infinity, it is 0. 1 over infinity, its limit is 0. Okay? That's the definition of little o. Little o, if the limit of the ratio equals 0, then we go back. Yeah, because although we use continuous variable, we will get back to discrete variable. After we find the limit, okay? So here, the thinking is this. When x takes continuous variable, goes to infinity, the limit is 0. Then we replace continuous variable by discrete. Now we can do it, right? We can do it. We replace. Then we have the limit, same limit, replace x by n, still true. Still true. Based on the definition of limit. Definition of limit allows us to do that. It's legal. Yeah. Yeah. All right. Example. Next example. Number 5. This time, n to the dth power. So here, this d greater or equal to 1. Yeah. Because here I want to use integer. Okay? Here I want to use integer. Yeah. Later we will know d is not necessarily integer. Any positive number, this result is true. But if we use integer, the proof is easier. Right? Yeah, proof is easier. Yeah. Not integer, we can still prove it, but we need one more step to prove it. Okay, just one more step. Yeah. All right. So now, still little o, we also need to take limit. Okay? Continuous variable, right? Yeah. So here we do not say those things. We just know it's a standard procedure. Yeah. So we know it. Yeah. Yeah. If you use x, I know it's continuous variable. Okay. So if you use n, I feel it is a discrete variable. Okay. Yeah. All right. Look, infinity over infinity, right? Indefinite, infinity over infinity form, we can take L'Hopital's rule. Yeah. The power rule derivative, yeah. So derivative, we use the power rule. Okay. Then derivative of a log, not log, exponential function. We have that formula. Okay. After that, you can see it is still an infinity over infinity indefinite form. Yeah. Still, infinity over infinity indefinite form. So we need to apply L'Hopital's rule another time. Yeah. One time, not enough. We need to apply it several times. See? Yeah. So second time, yeah. So here you see. Depends on how large is your d, right? If d minus 2 not equal to 0, we need to keep doing this until we get that d minus an integer equals 0. Then we can stop because it's not an indefinite form. Yeah. So we just keep doing, all right? At some point, we get d factorial, d minus d, okay? X to the d minus d, that's 0. X to the 0, that is 1. Now it is not infinity over, it is not an indefinite form, right? It is not an indefinite form. Oh, sorry, not indefinite. Indeterminate form. Yeah, indeterminate form. Yeah, you know, indefinite is nothing, right? Indeterminate form. So at this point, we need to stop. So you should not apply L'Hopital's rule anymore. Yeah. Then you'll get the wrong answer if you apply another time. You get a wrong answer. All right, so when we stop, let's simplify a little bit. We have this. Numerator is a constant. D factorial, it's a constant. Yeah, this natural log n to the d, also another constant. The variable part, a to the x, goes to infinity, so the whole fraction goes to 0. Yeah. Limit is 0. Okay. Then, based on the definition of little o, we prove n to the d belongs to little o of a to the n. Okay. That's the proof. Okay? Yeah. Yeah. So try to, get this pretty standard procedure. Yeah, pretty standard procedure. Yeah. Any question at this point? Yeah. All right. Now, after we prove this, but I want to generalize this d to positive number. Any positive number, we have this. Okay? Yeah. Because, so let me tell you the idea. How, for any positive d, how can we prove that? Any positive d, can we find two adjacent integers such that this d is between those two adjacent integers? We can find that, right? So now you based on that condition, you take L'Hopital's rule, you still do use the L'Hopital's rule. Okay? Yeah. You take, but at one point, you will get a negative exponent. Okay? Yeah, because that d minus 1, minus 1, minus 1, at some point, you minus another one, the x to that exponent will become negative. Okay? The first time it becomes negative, okay, that term is at a denominator. Okay? At that time, you can calculate the limit. Yeah. That idea. So if it's not integer, we can still do it. Yeah. But we need to do some careful treatment. Yeah. Careful treatment. Yeah. Using two integers, okay? L'Hopital's rule. Yeah. Yeah. So here I'll give you that idea. Okay? Yeah. So with that, later when we see, for example, square root of n, let d equals 1/2, square root of n. Yeah? Square root of n, this d equals 1/2. We still have this, right? Yeah? We can still use this. Yeah. All right. Example number 6. Square root. See? We have square root. Okay? Log of base 2. Now we want to prove this. Still the same, yeah. Limit, L'Hopital's rule, yeah. All right? Yeah. Derivative. Sorry. Yeah, all right. Before derivative, so here I just write another step. Yeah, before derivative, I want to write the square root as x to the power 1/2. Okay? Yeah. Because that will be easier to apply the power rule. Yeah. Power rule. We have a formula, power rule. So that's why we write in that friendly form. Now, let's take derivative. Okay? Based on the power rule, exponent number 1/2 times x to this number minus 1, so negative 1/2. It's okay. The power rule not necessarily applied on integer exponent. Yeah. Any real number, we can apply it. Okay. All right. Now, simplify. Let's simplify the fraction. We get that. This time, it is not an indeterminate form. So we cannot apply L'Hopital's rule, but we can already find the limit. The denominator goes to infinity, the whole fraction goes to 0. Now, our conclusion. Yeah. So conclusion, we go back to the discrete variable n. Yeah. So we have that limit, discrete variable n. Then our conclusion, based on the definition of little o, we have this. Okay? Yeah. So all 3 little o examples. Yeah. Limit. Okay. Calculate the limit. Yeah. L'Hopital's rule. Yeah. All right. Yeah. This Friday, I will post our assignment number 1. Okay. So I plan to give you a few questions like that. A few questions, yeah. But not too many. Yeah. Yeah. A few questions. Yeah. But also there are many questions. I check your understanding on asymptotic notations. Yeah. I created several questions on asymptotic notations, mainly the concept understanding. Yeah. So that part, I hope, based on the notes, based on the, our lecture, you can do that well. Yeah. All right. Next, we have more examples. Yeah. Number 7, natural log n. Right? Yeah. Similar to one of our previous questions. Yeah. But here you can see, yeah. This time, all right, d greater than 0. All right. This time the only difference is this d not necessary integer. Okay? Here you can look at the condition carefully. This d, we only need this d greater than 0. That's it. Nothing more. If that d is greater than 0, it is true. Yeah. So this result is very important. So I want to do here. Yeah. The method, the same as before. The limit, L'Hopital's rule. Okay? Take derivative, natural log derivative, very easy, 1 over x. The base e. So I hope you know the natural log. Base, we use that special constant, e constant. Okay? Its real value not important. Okay? You just know that special e is critical in calculus. Yeah. So that's the magic number. Yeah. E. Yeah. So then we have 1 over x. That's simple. Sorry. Yeah. And the power rule. Yeah. Denominator still the power rule. Right? Yeah. Formula. Yeah. Let's simplify the fraction. Look at this. See? Now, it's not a determinate form. Indeterminate form, right? So this time, x to the dth power, d is a positive number, any positive number. So when x goes to infinity, this function goes to infinity, right? Positive. We only need its positive. Okay? So the result, limit is 0. See? Limit is 0. Yeah. So why this is important? Because based on my experience, yeah, this result, yeah, when I give questions based on this result, it's very easy. Many of you will make mistake. Why? Yeah. So because here d greater than 0. It could be a very small number, right? Greater than 0. All right. How about we choose d? 0.000, many, many zeros. Okay? How about we choose 1 billionth? D equals 1 billionth. Okay? Very tiny, right? So n to the 1 billionth power. We use that function, we compare with natural log. Which growth function grows faster? Okay? Which function grows faster? Yeah. If you do not use this result, most of the students will choose natural log. Because based on their intuition, they feel n to the 1 billionth. It cannot be a large function, right? N to the 1 billionth, based on your intuition. Okay? Your intuition, 1 billionth, so small. Okay? Some students even use the software to calculate. Okay? Yeah, choose some n, then take 1 billionth power using some powerful software to calculate. They argue with me. Okay? So this number much, much smaller. But mathematically, when n goes to infinity, how can you test infinity, right? The students plug in some numbers and prove it's false, but your number is not big enough, right? Your number is not big enough. Can you try the number with 1 million zero? 1 million zero? You cannot, right? The student can never plug in a number with 1 million zero. How can you check it is false, right? So based on our mathematical proof, we don't need to plug in numbers. We know which one grows faster. Eventually, right? So that's why this result is very important. Okay? You can expect that kind of questions I will give you in the test, in the homework, somewhere. Okay? Based on this. Yeah. Because many times you do things based on intuition. Yeah. It's good. I mean, intuition is very important. We need intuition, but intuition, many times you get a wrong intuition. Yeah, it happens frequently. Right? So this one belongs to that case. Yeah. Intuition, not very reliable. Okay? Not very reliable. Okay? Yeah. All right. Next question. Number 8. N factorial. This is a tough one. Okay? N factorial belongs to little of n to the nth power. This is really tough. Why is tough? Because we need to estimate n factorial. N factorial. How can we estimate n factorial? Okay? Yeah, so complicated. Yeah. So we need to use a very special formula. Yeah. Because this formula, very, very advanced formula. So if you are familiar with calculus, you may see it in your calculus class. So I don't know, so probably 1900, yeah. It should not be in 1800, 1900. Probably, so because I didn't teach that class. So Stirling's formula. Stirling's formula. We need this. Yeah. Stirling's formula gives us really good estimation of n factorial. So let me give that inequality. Okay? Yeah. N factorial approximately equals to this. See? See? The magic, How can you see that, right? Approximately equal, yeah. But that approximately equal, not good enough. How do you approximate, right? How do you approximate? So we want more precise than that, right? All right, so we use inequality better than this approximate symbol. Yeah. So this is a better estimate because we use upper bound and lower bound. See? Upper bound, lower bound. Okay? Then when we take limit, it's much better, right? Because if you use this approximate, when you take limit, what's that? We cannot control it. Right? That approximate symbol, what's the meaning of that? We cannot control it. But if we use this inequality, we can control it. Right? So that's why the bottom formula more useful. Useful. We can take limit. Yeah. All right. Now let's take limit. Okay? When we take limit, we use both lower bound and upper bound. Okay? We do the fraction. Okay? So this representation between two fractions. Okay? Yeah. So we get upper bound, lower bound. So we estimate from both sides. That's better. Okay? Both sides. Yeah. All right. Now let's take limit. Okay? Here I take limit. Yeah. So we take limit. Yeah. So we also have this inequality, right? Yeah. But be careful, this unequal sign, but when we take a limit, you need to add equal. Okay? Yeah. Unequal, when you take a limit, equality is possible. So do not miss that equality. Yeah. All right. Next, cancellation, simplification. All right. So here, Can you tell me immediately the limit of this based on our previous examples? We learned so many examples. Is there one we can use? Yes. If you do the real calculation, we need to change. Yeah, that's good. Okay. But here, my question is, you just use our previous result because we did that before. Why we need to repeat it? Okay. Can you use our previous result? We can quickly answer the question. Do you remember one of our questions? Just in one of the examples today. Yeah? One of the examples we just learned today. Which one do you feel can be applied? 2.4. Yeah. 2 point something, whatever. But that n to the dth power compared with a to the n, right? Little o. N to the d belongs to little o of a to the n. That example. N to the d. This n to the d. d 1/2, right? A to the n. A equals z, right? Apply that one. Okay? Little o. That one little o. That means this limit is 0. This limit is 0. How about that? Okay? Yeah. Yeah. That example. Yeah. The general case, that means we can extend that d to any positive number. Okay? Any positive number. Yeah. Not necessarily integer. That's the general means. Yeah. Because this question, our d is integer. So we generalize it a little bit. Okay? We generalize it a little bit. Yeah. So we can apply it. Okay? All right. So apply this one, the result 0. Yeah. Yeah. Limit 0. Yeah. Actually, I should write this equals 0. Okay? It's better, not greater equal to 0. Let's write equal to 0. Okay? This one equals 0. Okay? That one equals 0. Okay? 0 from upper bound, 0 from lower bound. What's that? 0. Okay? Based on what theorem? There is theorem in calculus. Okay? That's squeeze or sandwich theorem. Sometimes people call squeeze theorem. Yeah, you squeeze from two sides. Squeeze. Some people call sandwich. So you get sandwich, right? Sandwich, okay? Yeah, these two names. This is a powerful, powerful method in calculus. Squeeze or sandwich theorem. Very powerful in calculus. Okay? So now we can get a conclusion. This limit equals 0. We prove that, little o. We prove that little o. Okay? Yeah. How about that? Yeah. You can see. So that's why I say this question, very hard. Okay? This question, very hard. Yeah. The reason you need to use a lot of math knowledge. A lot of math knowledge. Yeah. Okay? Yeah. All right. So any question? Yeah. Very good. Okay. Then, if any question related to factorial, you come back to look at this formula. Okay? Yeah. Because from now on, I may give you questions related to factorial. Yeah. Factorial. Yeah. All right. Next. Yeah, we have, our last slide for this part. Yeah. So I try to give you more examples. Yeah. Probably the last, number 9, yes, I do not know. Yeah. Yeah, so this is from textbook. Yeah. What's that? For each of the following functions, indicate the class big theta of g of n, you need to find a g function the function belongs to, because below you will have A, B, C, D options. Use the simplest G function possible in your answers. Okay, all right. Let's look at the questions. A, this function, it belongs to big theta of some G, simplest G. So which G function do you think we should use here? That one. Okay? So for a question like this, still dominant term, right? Plus 1 we can ignore. Let's take the dominant term, n squared. Okay? N squared to the 10th. So, 20. Yeah. Not 10. Yeah. 2 times 10. 20. Yeah. Sorry. Yeah. I need to correct it. 20, okay? Yeah. It's wrong. Yeah. All right. So I will modify this slide. Yeah. Dominant term. Yeah. B, square root of a quadratic function. What big theta class does it belong to? Okay. Let's take the dominant term. All right. Actually, we can skip that constant. We don't need to include constant. Okay? We take this, but constant in this situation is not important. So n squared, you take square root, big theta of n. Big theta of n. Okay? That's simple. Okay. C, this function, a little more complicated. A little more complicated. What big theta class do you want to use to describe this function? Okay? What big theta class do you want to use to describe this function? Okay? Yeah. So here we have two terms. Which one is more dominant? Right? You answer that question. Two terms. So which one is more dominant? So which one dominates another one? Let's say in this way. Which one dominates another one? The other one. Okay? Yeah. So then we drop the other one. Okay? Yeah. We just take the dominant one. Okay? Yeah. Because it confuses you a little bit, right? Confuse you. Here we have a square here, but we also have a square here. Okay? So how do we compare? Right? Yeah. All right. The answer is that one dominant. Why? So let me use a property of logarithm. Logarithm. Okay? The square here, there is a property we can use. Based on the property, this exponent 2 can be bring down to the front. Okay? That's the property of logarithm. Then square is gone. You just get a constant. Okay? You just get a 2 constant. We know constant is not that important when we compare which one is dominant, right? The constant factor is not that important. Okay? We can ignore, right? So, but this 2 you cannot ignore, right? This exponent 2 you cannot ignore. Okay? So because after you make that constant, this log n plus 2 just is similar to that part. Yeah, yeah. I mean, log over 2, n over 2, but n over 2 based on another property of logarithm minus 1. Okay? Minus 1 is a minor term, right? So not very important. Minus a constant we can ignore. Okay? So you have log here, you have log here, right? The plus 2 not very important, right? Plus 2 minor, very little. Okay? So you have log n here, log n there, equivalent, right? But in front of log n, you have a square term, but here linear term, right? Definitely square term is larger, much larger than the linear term. So that's why this is our dominant term, new dominant, our current dominant term. Right? Yeah. Big theta, when we choose big theta, we can drop this 2 and we can drop that 2. Right? Not important, not important. The remaining, the simplest possible g function we can get, after all the simplification, we get this answer. How about that? Okay? How do you simplify the g function? G function. Okay? As simple as possible. Okay? But make sure you do not drop the critical constant, right? Important constant. Don't drop those 2, okay? That's critical. That will change the order of growth function. You'll change the order of the growth function when you drop those 2. Don't drop. When we drop this 2, we do not change order of growth. When we drop this 2, we do not change order of growth. But that one will change order of growth. Okay? Yeah. So that's the key point. Yeah. Order of growth. All right. Yeah. D, the last question of this example. Yeah. 2 exponential functions. The first one we use base 2. The second one we use base 3. Okay? But exponent slightly different. n plus 1 here, n minus 1 there. Yeah. So which one is dominant? Still, the same question. Which one is dominant? So we take that. Yeah. Base 3, right? Base 3, much larger. Okay? Although exponent slightly smaller by a constant. Just by a constant. Okay? So this one is more dominant. Can you see that? Why this is more dominant? Oh, so you can see. Yeah. Yeah. So that's why our big theta class is that. Big theta of 3 to the nth power. Okay? I hope you have no question. If you have, just ask me. Okay? I will answer immediately. Okay? Yeah. Otherwise, I will pass. Yeah. Okay. Any question? A, B, C, D? Anyone? No. You can ask. Yeah. Then we will move on. If no, no. All right. That's it for our lecture 2. Oh, we have you. Oh, sorry. I forgot. Yeah. Oh, that's a special function. Floor function. Yeah. Floor function, you know, the difference with the original function, less than 1, right? The floor function. Because you only drop the fraction. Less than 1. So less than 1, so then let's just drop it, you know. We drop a fraction. It's not a big deal. Right? So that's why. Yeah. All right. Okay. But here I want to give you change of base rule for logarithm. Yeah. Because you look at, we use many different log base, natural log E, so many different log bases. So sooner or later, you need to use this change of base rule. Here I just review a little bit. Okay? So base A, we can easily change to a different base C, but it will change. You need to write in this fraction form. In fraction, this form. Yeah. Change of base form. Okay? Yeah. Yeah. So here you can see we have so many formulas. Yeah. Yeah. I haven't put them together. Yeah, but you know, because I will assign you homework this weekend, so I should make all the formulas available when you work on your homework assignment. Yeah, because you need to use all these formulas. Yeah. Yeah. All right. Now we finished that lecture 2. So let's move to